talk of this session is going to be by Daniel, who's going to tell us what does it mean for a compiler to be correct, in particular if that compiler is not compiling a whole program, but just a part of it.
Hi. So compiler correctness is an old problem. In 1967, John McCarthy and James Painter wrote a paper that laid out the essential issue, which is that it doesn't matter what reasoning, formal or informal, you do about a program if you then compile it to a program that does something different. And so the theorem that protects against this, we've had this theorem for decades, and it's usually called semantics preservation. And so the idea is that if you have some source program, PS, and you compile it, and I'll use this squiggly arrow for compilation, you compile it to a target program, PT, then you essentially want that the behavior of PT refines the behavior of PS. And so that means that you run PT and whatever observations, whatever output to the screen, whatever value result from PT, that also is true of PS. So compilation should preserve meaning. And this we've had for a while. There's actually a diagram in a paper by Lockwood Morris that was published in Popple #1 in 1973. And this same diagram could be used to understand the correctness theorem from Xavier Leroy's CompCert C compiler that was first published 35 years later. But there's a problem, right? Because we don't compile whole programs. We compile parts of programs and link them against a standard library, or we compile our programs as separate modules and then link them together, or we use FFIs, or we have an inline assembly. And so the question is, if you compile an individual module, which I'll write as ES, into a module ET, and you complete that into a program by linking against some target code ET prime, then what is a correctness theorem for this compositional compiler? And intuitively, what we want is that ET prime linked with ET should sort of be the same as ES linked with ET prime, right? That's what we mean, that really we want this refinement between ET linked with ET prime, and I'll use this bow tie to mean linking. ET prime linked with ET should refine the behavior of ES linked with ET prime. And that's what it would mean if ES and ET sort of meant the same thing. But what does that even mean? What ES and ET prime aren't even written in the same language. And so one question that you have to answer if you're working on this is, how do you link source and target? And so different papers, people have been working on this for years, and different papers have produced remarkably different answers to this question. They've done it with different formalisms, and they've come up with often very different theorems. So not just that the proofs are different, but the theorems themselves are different, because sometimes they'll answer this by directly giving you some way of linking together source and target and giving meaning to this. Sometimes they'll answer it by sort of having this statement actually translate the target back into the source and then give meaning by having a source program that is refined by the target. The other way that results have differed is, what can you actually link with? Because there are lots of different answers. Maybe you can link with everything in the whole world, but oftentimes there are a lot of restrictions that need to be made in order to actually state the correctness theorem that you have. And so we're in this world where there's lots of different results, with lots of different approaches, with lots of different formalisms used for it, and they have lots of different answers to what can you link with. This spectrum is sort of along the lines of what target code can you link with and where does it originate from, which extends all the way from nothing for whole program compilers, and there's tons of whole program compilers, CompCert, the original CompCert, just an example here, or the output has to be from the same compiler, all the way on the other end of the spectrum is you could link with code that you couldn't even express in your source language. And so our contribution with this paper is to give some kind of unifying statement of what do we mean by compositional compiler correctness, and give it so that we can then unify and force individual results to give an answer to these questions of like if we actually have this one statement that we can then instantiate in different ways, we can actually answer this question of how do you link source with target? What in your result is your answer to this question? And what exactly do you allow us to link with? So how does this work? So our theorem, Compositional Compiler Correctness, or CCC, we can look at it as sort of trying to actually piece together that picture from before. So if we compile a module ES into ET, then we want to link it with some other code ET prime. And I'm using the same bow tie here, but I want to be more precise about the actual languages that we're linking. So the T on either side is we're linking T code on both sides. And a particular formalism, a particular result needs to tell us what is it that you can link. Where does this ET prime come from? And so you should provide us a set that tells us, what is acceptable. And so that's what the linking set is. And in particular, different results might actually require you to provide some additional evidence saying this target code is acceptable. And that's what this phi is. It's a witness to the fact that this target component is something that we can link with. So this additional proof term or witness phi is there. And then we need to provide something, if we're thinking about refinement between whole programs, we need to have something that corresponds to this ET prime in the source, except for it may not actually be the source. And so I've written in gray here because there's a huge variability in existing results. And to account for that, what we say is, well, that we'll call S hat. It's the linking medium. It's some way that we allow you to link the source to the target. And what you need to do is provide a way of translating the target component you're linking with ET prime up to that linking medium, which is what this function lift is, the double up arrow. And then you need to give us some way of linking between source code and code in this linking medium. That's what this link with S and S hat is. And note that the actual lift function, it's existentially quantified. There's more details in the paper, but essentially the point there is someone reading this theorem doesn't need to read the details of the lift function. It's not sort of in the trusted base. Assuming you have that, then the refinement that the actual correctness statement for the theorem is, as we would hope, that ET linked with ET prime refines ES linked with this lifted ET prime. And so what people have to do, the way to use this, is provide us an answer for what is the linking set, what is the linking medium, what is the lift function, how do we link this? And just as a note, whole program compilation, separate compilation, they follow as consequences. We would expect this. This is supposed to be a stronger statement. If this weren't true, there'd be something wrong. So how do we use this? I want to go through a little tour in some of these papers just to show you how we can instantiate our theorem from these results and sort of use that to compare and contrast and see what we can learn. So towards the left, this is a paper by Jihun Kang and collaborators. SepCompSert was an extension to the CompSert C compiler. And the idea here was they wanted you to be able to do separate compilation. They wanted to be able to compile individual modules and then link them together and have that be the same thing as if you would link them in C. And this was incorporated into CompSert as a version 2.7. So if you're using CompSert now, you're using the results of this paper. And so how do we do this? So for SepCompSert, the linking set said, well, we can link with any output of the SepCompSert C compiler. So our target components, ET, are anything that was compiled with SepCompSert, and so in particular, this witness phi is the source code that was compiled to that particular target. That's what we need to know in order to know that this is okay to link, that it actually came from the SepCompSert C compiler. But our linking medium, it's just the source. There's nothing special for SepCompSert because the lift function gives us back that witness itself. So the refinement for SepCompSert ends up being between a whole source program and a whole target program, right? And so we can see this instantiation, sort of some parts of this end up being, well, it's just a source program, and that's fine. We plug these in, and then in the paper we prove that this general property of the refinement we have follows from the proofs that they did of correctness. So moving further along on the spectrum, the Pilsner compiler, which was by Georg Neis and collaborators, they were aiming for a little more flexibility. The idea was that you want to be able to link with code that didn't necessarily come from your compiler. And they even have results in the paper where you could have code that was handwritten assembly, but it had to be related to some source code. And this is work that's building off of cross-language logical relations, correctness results. And so the idea here is that what you can link with are any target components where there is some source component that is related. And so the cross-language relation they have, the PILS relation, is how you relate source to target. And so as long as you can provide some witness, some source component that is related to the target code you want to link with, then that's fine. That can link. And again, like subcompcert, the linking medium is just the source language because this lift function can produce a source component for you. And that's what we need. The linking medium is something we need to be able to link to do the refinement. And again, we proved that our refinement follows from the proofs they did in the paper. The third paper I want to look at is Compositional Comp. This is by Gordon Stewart and collaborators, and they were trying to provide a much more flexible notion of compositional correctness for CompCert. This is not part of CompCert as yet. And they did it by essentially defining a way of be able to call between languages, between the different CompCert languages. They have a protocol where you can make cross-language calls. It's dependent upon the CompCert value and CompCert memory model, but any CompCert languages and anything sort of like that could fit in. And what that means is that they can link, their linking set is any target code. Any target code is fine. You don't need to prove that it's related to anything. But this comes at a trade-off, which is that the linking medium is now this language-independent interaction semantics. Interaction semantics is their way of having these cross-language calls. And that means that because you can directly link source to target with this interaction semantics, our linking is just adding things together, and the lift function is just take the target code. And we have now a refinement that's really directly what we had in this original picture, source linked to target, target linked to target. But it comes at sort of a cost, which is that understanding this theorem, you have to understand this interaction semantics. And you have to trust that it's right, because this is part of the theorem statement itself. This is not part of the proof. This is part of the theorem. So if there's a bug in the specification of this interaction semantics, the theorem could be entirely wrong. It's a risk. And so the last result I have on the spectrum is a multilanguage compiler by Jamie Perconti and Amal Ahmed. And what they were trying to do here was essentially they wanted a compiler where you could link with code that you could not express in the source, which is something that none of these other results had. And they did it by setting up what's called a multilanguage, which is where you embed the source and the target syntax into one language, and you introduce these language boundaries that mediate interaction. And so the way that this works for our CCC theorem is the linking set is any target component that is of translation type. And what that means is that it's target code, but it has a type that we can interpret as a source type. So at the interface, we can interact with this as source code. Internally, it could do whatever it wants. And the linking medium is this multi-language. That's the formalism they used. It's a multi-language so that you can actually link together in the multi-language, and so that the actual lift function, what it does is it takes target code and wraps it in this boundary. The ST is the boundary itself, S on the outside, T on the inside. So there's target code that's wrapped up in a boundary, which means it can be interpreted, it can be used in a source context. And that's the reason why the restriction is that the target code has to have a translation type, because if it didn't have a translation type, we couldn't put it inside a boundary, we couldn't use it in source context. And so this, again, like compositional CompCert, we sort of ended up with a trade-off where we can link with a lot of things. And in their paper, they showed they can link with code that could not be expressed in the source language. And that's really good. I mean, that actually, when we think about real compilers, oftentimes why we're linking is to try to get access to things we don't have in our language. But it comes at sort of a trade-off, which is that the linking medium is now this completely new multi-language. And so you have to understand, how does this multi-language work? How do these boundaries work? What is the operational semantics of this? Is the fact that the refinement is between the semantics of this multi-language and the target, does that actually make sense? Does that make sense as a correctness statement for me? So stepping back, the point of this tour, and obviously, this is 4 papers out of an area that has many more, is that there's a lot of different formalisms. There's a lot of different theorem statements. There's a lot of different ways of approaching this problem. But we can sort of start teasing things apart with this definition. We can see it becomes a lot more easy to compare both how can we use the theorem, what obligations does it make on us, and also then what do we have to understand? What do we have to trust about the theorem in order to use it? Another thing that sort of comes up that I think is very interesting, that's sort of more in the future work realm, is for multipass compilers. So most real compilers have multiple passes. And so the idea is if you have a source component ES and you compile it to some intermediate language EI, and then you compile that to a target component ET in the target language T, if you actually prove that each of these passes satisfies our CCC definition, and in particular, you prove it where each of the lift functions is actually a back translation, which Thomas was talking about. And what that means is that the linking medium is actually the source language. So this is I, not I hat, and it's S, not S hat. So we actually have a way of translating back, and there are no proof terms, it's just ET. If you actually have a way of translating target code to intermediate code to source code, and you've proven these compositionally correct, we can prove in general that a two-pass compiler composes into a multipass compositionally correct compiler. And this is interesting both because oftentimes there's work involved in proving this transitivity result, but I think more importantly, this is true regardless of the method you use to prove each pass. So you could prove the first pass using one method because that made sense for whatever languages they were, and you could prove the second pass using a completely different method. And the composition still works. It doesn't have anything to do with because you've sort of abstracted over, you have this general theorem, and that's the only thing that's realized. Like this proof is an abstract. And I think it's nice if the modularity of our proofs could match the modularity of our compilers. We can prove compilers. We can write compilers pass by pass. We can add a new pass to a compiler without changing existing ones. And that's not generally true with the way that we prove compilers correct. Generally, we sort of have to think about what are all the passes, what are all the things they involve, and then let's prove all the passes correct. And obviously, this is future work, but we think it's sort of an interesting consequence of sort of doing this kind of thing. So there's been a lot of work in compositional compiler correctness, and there's going to be more. But currently, it's a huge effort on reviewers in particular to understand sort of the particularities of formalisms and the details of, what is your theorem statement and how does it relate to all the other theorem statements and all the other formalisms, because none of them really look similar. And that's hard. And we really think that if people actually take prove your compiler correct, but then show that it satisfies this general definition. And not only will you probably realize, yes, this is actually compositional, you get that benefit, but I think you'll make it a lot easier for reviewers not only to have a high-level understanding of how your paper works, because they get these parameters, but to much more easily compare it to other related work. And we think that would be great in this area where it's been really, really hard to sort of compare across different results. So, thank you.
We get the mic there. First question from Slido. You said something along the lines of like lift isn't really that important to show or something like that. That's not really in the trusted code base. But are there any additional requirements on it? Like, do you require that it compiles to equivalent code in some sense or something like that?
Yes, there are additional requirements. They're in the paper. There's some side conditions on the properties. You essentially need it to be behaviorally an inverse of compile. That's sort of the intuition, but there are details in the paper. The definition is more formal than what I could fit on the slide, but not that much longer.
So when you talk about multi-languages, does that cover all of the richness of FFI? Like if you've got a couple of runtimes coexisting and things like that?
I am not aware of work that people have done to formalize multiple runtimes using multi-languages. That sounds exciting, but yeah, I'm not sure. I mean, the multi-language is specifically, it's a syntactic approach to combine multiple source syntaxes and operational semantics. There's various properties around that and boundary terms. If you're looking for it, it came originally from a paper by Findler and Matthews in 2007. So, 6, 7.
Is there any instantiation of your theorem that you cannot express as a full abstraction result with the right instantiation for the equivalence relation?
In general, there's not an equivalence relation. These are all refinements. So I'm not sure exactly what that question's about.
I have a question. We're here.
Yeah.
First of all, this was a very clear talk. Thank you. I'm trying to understand. So you give a nice formulation of the comparisons between existing work. What I'm not quite getting at is whether you found some new insights or some new observations about the relations between existing work that wasn't already known. Because from what you presented in describing the different papers, that corresponded to what I thought was the general understanding of those papers.
I think probably it is an understanding among a small number of people, which you're certainly one of.
Well, the people who read all the papers, yeah.
Yeah. I think that the intuition about multipass compilers and the potential impact that bothering to do full abstraction proofs might help the sort of vertical compositionality and the transitivity proofs. I think that might have been new. But in terms of new observations about past work, not necessarily. I think it's a lot easier to compare them now using this, but yeah.
What do you think would be the most promising way to address cross-language compilation for the ecosystem of LVM-based languages, like, for example, linking Clang code with Rust code in this framework?
I'm not sure. I mean, we didn't really look, like the actual how do you prove the correctness of a particular compiler is not really in scope, right? What we're trying to say is like, how should you state the theorem? And so I think a theorem for compiling Rust to Clang, I would expect you could formulate it in this way, but yeah, not sure.
It's really nice to see somebody trying to systematize an area of work, especially one with as much work in it as this. I want to thank you for doing this work.
You're welcome.
It's really neat. I get the impression that it was just simple enough that if you didn't have the Perl category, that you couldn't do this. So the question is, did Perls help you to do the systemization? If so, yay for Perls.
Sure, yeah. I mean, I think Perls are great.
Could you have done it if it wasn't a Perl? If Perls didn't exist, could you still have done this work confidently?
Maybe, maybe not. I mean, I think that part of the goal was to not try to spin out significant novel research, but to actually try to focus on what is the essence of sort of distilling all of this existing work to the point of which, like, making something that's easier for people to reuse. So I think if we did sort of build a bunch on to make it be more significant research, then it may have been harder for people to reuse. So that's, in that way, maybe that framing does help. And I don't know. I
And
think that the
makes it
idea
sound
of
like pearls are
Yeah.
serving a useful role there.
yeah, I think they are, and I think the idea of like we were thinking about this as a theoretical Perl. I think that framing is very useful, and maybe if Papa wants to take that on, that'd be great.
Well, in that sense, thank you very much, and have a nice break, everyone.